Welcome to qnawire.
Chapter 16, problem 114, chemistry is the central science. So the question gives us two equations for glycines, for the Ka and for the Kb when in equilibrium with water. And the first question asks us to use the values of Ka and Kb to estimate the equilibrium constant for the intermolecular protein transfer for the zero orbital ion. So to do this, we know that our K equilibrium is going to equal to Ka times Kb. And whenever you plug in our numbers from that is listed above, you do 4.3 times 10 to the negative third times 6.0 times 10 to the negative 5. And when you plug that into your calculator, you get 2.6 times 10 to the negative 7. And so that is going to be your answer for part A. So for part B, it's asked us what is the pH of a 0.05 molar aqueous solution of glycine. And so to do this, we're going to have to use an ice table and a Ka value to be able to get that answer. So the first thing we need to do is write out our equation to be able to get this. So we're going to do is we have our H3N CH2COO minus, and this is going to be plus our H2O goes to NH2, sorry guys, goes to H2N CH2COO minus plus H3O plus. So now that we have this, we can now figure out what our equation is going to be. And we can use our ice table from there. So we know we have an ICE, and our initial concentration was 0.05. Since we have water, that does not play a role here. And also we had zero starting concentration off for our H3O plus. So now what we're going to do is then write in the exchange that's going to happen. So we're going to subtract something from the initial concentration, and then we're going to add that to the other side. And then we're going to have the equilibrium where we add the two up. So 0.05 molar minus X, and then X. So the next thing we have to do is actually find our Ka value, especially since we have that H3 plus, we know it is a Ka and not a Kb. And to be able to find our Ka, we had to use the equation given above that. We had to use the equation Kw is equal to Ka times Kb, where Ka is going to equal to Kw divided by Kb. And so whenever we plug in our values, we get 1 times 10 to the negative 14th divided by 6 times 10 to the negative 5. We get a Ka value of 1.66 times 10 to the negative 10. One thing to note is that since our Ka value is very small, it's going to make an insignificant impact onto our 0.05 molar solution. So we can just get rid of that X to make the math a little bit simpler whenever we're doing finding for it. So we have our Ka is equal to our products over reactants. And so we're going to have X squared over 0.05. And the X squared comes from multiplying the NH2 to CH2COO and then the water concentrations together. And that is equal to the 1.66 times 10 to the negative 10. And then all we had to do is solve for x. So x squared is equal to 1.66 times 10 to the negative 10 times 0.05, all taking the square root. We get the value of x to be 2.88 times 10 to the negative 6. Now, having that 2.88 times 10 to the negative 6, that is going to be our H plus concentration. And since that H plus concentration is important to have to be able to find our pH, we can then just plug this in to our equation to find our pH. So all we have to do is our pH is equal to a negative log of 2.88 times 10 to the negative 6, and we get 5.54, and that would be our answer for part B. And then part C is just asking us what would be the predominant form of glycine in a solution with a pH of 13, and what would it be in pH of 1. So what you're wanting to do here is you want to see which one's going to be the most basic form and which one's going to be the most acidic form. And to do that, you can just look at the charges of them as well as your Ka and Kb. So for pH of 13, the H2 in CH2 minus CO is the most basic form of glycine, where the H3N minus CH2COOH is the most acidic form. And the reason is because it's more able to donate those protons, where here we already donated 2 protons, and so it's in the most basic form.